happy to introduce Tianyu. Tianyu is a PhD student at Statistics Department of UC Berkeley, and under the supervision of Professor Michael Jordan and Professor Song Mei. And Tianyu's research interests focus on causal inference and the theory of machine learning, and particularly the theory of large language models. And yeah, very happy to have Tianyu talk about his latest findings about the mechanism of LLM.
Thanks so much for the so today I'm going to use the title of understanding language models as like physicist, but this physics is purely based on like a statistics PhD's imagination. Well, but it's like it's a useful metaphor, and it can actually give us many interesting findings. This is based on works with a lot of my excellent collaborators. So the next, could you change the page for me? Oh, so okay, so I should start with a little bit discussion on how to understand language models. And there's actually a spectrum. It might be a little bit cliche for most of you. It's like on the one side, it's mathematician. We are happy to work on small models, it's easier to analyze. It's good, but people always suspecting that it's just understanding shallow neural networks, right? Just 2-layer neural networks or several layers. And on the other hand side, it's how engineers work. They are given a pre-trained language models, and they use a lot of experiments to see how it works. So it's very hard, and normally all their conclusions are not very solid. But that's what the really useful thing. They are trying to understand real models. And so recently, these ideas of physics language models have become very popular, proposed by Zeyuan. And so what they do is to train small middle-sized model, which means like GPT-2 sized, and on synthetic data for specific task, and experiment to see how it works. Oh, well, and it's great because it's solid. It's in control settings solid, and also many of the tasks they consider are very practical for real world. But it also has some problems. It's like, if we think about it, it's a GPT-2 size model. It's still really hard to analyze, and it's we couldn't use any mathematics for it. And also, it's still a middle-sized model trained on synthetic data set. It's not understanding real language models trained on web data. And there's still a gap between the two. What I'm going to say here is like working at the middle using the idea of physics and language models still is not entirely satisfactory for us. And so what's our approach is that we want to kind of work on a circle instead of staying in the middle, which means that, okay, the animation is a bit broken, but that's the idea. It's like we sometimes want to be engineer and sometimes want to be mathematician. And more concretely is that we will start with observations in language model, make hypotheses, and do experiment in very controlled setting, and analyze it in a very fine-grained way. Then we would make concrete and easy to verify the predictions in language models. So with this methodology, a good understanding our goal is to give exactly matching, and it should also be quantitative results between the small models trained on synthetic data set and our large models pre-trained on web data. And okay, to be honest, it's a really high bar. And I think a lot of theorists have given up on this direction. They're happy to work on small models and prove theorems. But to make things useful, we need to try to work on the cycle and bridge the gap. That's what we are trying to do. And we found that it's actually pretty doable. And so today I'm going to present two concrete understandings based on this methodology. And the first one is called random guessing mechanism for two-hop reasoning. So let's start with the observation. And this is a prior work by Google, and it's actually quite impactful, is that language models can be easily distracted by irrelevant contexts in reasoning problems. For example, this is the original math problem, and they just impute some irrelevant context to distract the transformer, to distract the language model. And here's the result. So basically, accuracies are roughly 100% without distractions. So with distractions, they all decreased to around 70%. And our setting, actually, we are considering a more narrow setting. It's like we only focus on two-hop reasoning. By two-hop reasoning, we mean that it's something like this. A is the father of B, and B is the father of C, and therefore A is the grandfather of. So A to B is a one-hop connection, and the grandfather is a two-hop connection. So the transformer, the language model should find B and find C to predict the correct answer, which is C. And it can actually do this with perfect accuracy. And a very interesting thing is that as long as we have some distraction, so here we just impute some irrelevant information, say like D is father of E is father of F. Nearly all the language models that we evaluated, we found that they will just random guess between the answer C and F. So we want to understand why it happens, and more broadly, how do language models to perform two-hop reasoning? Actually, some people from more theoretical side, like Sanford, Daniel, and Matus, you see all the theory people, they have proved something that transformers can use log k layers to solve the k-hop reasoning problem. And they prove a lot of theorems on it. And we call this their conjecture, their hypothesis as log k algorithm. So we would take this as our initial guess. Then we will go down to the synthetic data set and to do controlled experiment. So here we consider input format with this kind. So this square is our source, and the triangle, and this is we have three entities: the square, triangle, and the circles. And we have a query token which is square, and you see based on this connection, square to triangle, triangle to circle, the expected answer of a two-hop reasoning should be the circle. And the right ones are just distract information. The blue ones is our target. And each time we reshuffles this context information, reshuffles the label, reshuffles the order, and the train transformer on computing the loss on the expected answer. And sometimes, okay, we call the square as source, triangle as bridge, and the circle as end. And also each one-hop relationships, we would call them parent and child. So these are some terminologies that we use. Yeah, it's quite intense here, but it's good to just have an idea like, okay, this is our format. We have many two-hop trains, and we have three entities. And it's a fully in-context problem. So here I'm going to present the first result. It's the training dynamics for the three-layer transformer. So the blue line here is the probability of predicting the expected answer. And the purple line is the probability of predicting the distracting answer, which is the right ones, right circles. And the green and the yellow ones are probability in context or other tokens in vocabulary. And immediately, there's some interesting pattern here, is that from approximately steps 100 to 800, it's a slow learning phase because the accuracy actually grows very slowly. And also, the blue line and the green line, the blue line and the purple line, which means the probability of predicting the correct answer and distractings, are very close here. So it's just guessing between multiple two-hop chains. And then the transformer would go through a sharp phase transition, and suddenly it could reach a 100% accuracy. And we call it a sequential query, which I will introduce later. So any questions so far, just to make clear the context that we are considering? Okay, cool. So now we always work on 3-layer transformers. And so I'm gonna just give the takeaways first. The first takeaway is that there's a mechanism that we call it sequential query that transformer uses to solve the two-hop reasoning task. And the second takeaway is that the theoretical construction by Sanford at 2024 actually is wrong. So the transformer does not learn their theoretical log k mechanism. And the takeoff 3 is that we actually can fully understand how transformers make random guessing, but the details will be omitted because of the time limit. So let's start with talking about the sequential query mechanism, like how does 3-layer transformer perform the two-hop reasoning. So the first thing that is worth to know is that actually, even if we are training this 4th 3-layer structure, the MLP layers are always neglected by the training dynamics. So which means like, okay, we take the checkpoint at step 400, and when we do the forward pass, we skip MLPs, the accuracy is still the same. And we take the checkpoint at 10,000, it's still the same. So the training dynamics is like, they never care about MLP layers. So let's make things easier and skip MLPs. So what happens in the first layer? So here's the attention plot. You see it has a clear pattern. And this clear pattern is just every child token would look at its parent position and copy the information to them. So it's like a copy or the first layer in induction height. And what's the second layer is doing? The second layer, because we have done the copy, so in this case, the bridge, the triangle, has the information of its parent, which is the square. And our query is also the square. So it can find the triangle here and copies information to it. So the query token looks at the bridge token in this case. And you see here's the attention pattern. The bridge token is here, and all the attentions are concentrated on it from the query token. And actually, this is exactly what induction height is doing. So I'm not sure if you have read the blogs by Anthropic, and they talk about induction height, which is the key for in-context learning. And the first 2 layers are exactly implementing the induction height here. So what does the 3rd layer do? The 3rd layer, based on all the information from the previous 2 layers, now the square knows which is the square. Now the square has the information for the triangle. And also because of the first layer, the circle also stores the information of the triangle because triangle is its parent. So then our query can correctly find the position for the end token, which is here, and copy the circle to that position. And this gives us the correct prediction because that's what we want to predict. It should be the circle here. Yeah, so this is how sequential query works. Any questions so far? Okay, so the takeaway too is that the theoretical construction actually is completely inaccurate here, because in the log K hypothesis, in the second layer, it should be completely a different mechanism. And actually, this proves that the three-layer transformer does not learn the log K mechanism constructed in theory. And the third takeaway is that actually there's a very interesting mechanism for random guessing. It's quite complicated, and I don't expect that we can catch it in this talk. The conclusion is basically that if we want to put it in one sentence, like the random guessing is made possible because the end tokens can surprise the prediction of bridge tokens, which means circle could surprise the prediction of triangles. So this would lead to uniform guessing only between unended tokens in the context. Well, so the three takeaways in a shorter version would be, first, the sequential query is how transformer solves to hop. And takeaway two is like never believe the constructive proof by mathematicians. And the third is that the random guessing mechanism is actually pretty interesting, but we don't have time to cover it here. So let's go back to large language models. As I promised, everything would find perfect match in language models. So the first quantitative prediction we have is that when there are k two-hop chains, with k minus one of them being distractions, and then language models would predict each end token with probability 1/k. So it's a very exact and quantitative prediction. So we need to come up with some methods to evaluate. So we ask language models, of course, to design real two-hop reasoning settings covering several topics. For example, so for family relationships, it will be A is the mother of B, B is the mother of C, and we ask about the grandmother. And also for biological taxonomy, so say like A is a species in the genus B, and B belongs to the family C, and we ask about the family of A. So it's a two-hop reasoning related to biological taxonomy. And we would add distractions onto based on this template. So say we want to have two-hop chains, then we would just insert an irrelevant information, say like D is the mother of E, B is the mother of F, into this ABC chain. When there are three, we just insert more, like D, E, F, H, I, J, something like this. And also, we make it even longer, like 4 two-hop chains and even 5 two-hop chains. Then we would replace all the placeholders with fake names and reshuffle the order of sentences each time. And by this method, we can get 1,000 samples for each k two-hop chains. And here's an evaluation in almost 7B. So when there are two-hop chains, the prediction probability for the target and distraction are exactly the same for all the topics that we are considering. So by target, it's just C, and distraction, we mean F. So you can see only in the biology, it's prefer the true answer C, but in all other cases, it's just random guessing between the two answers. And also, if we have more two-hop chains, like from 2 to 5, the probability of getting the target is exactly following the 1/k scale. And we also try this in Llama 3.1. Okay, when there are two two-hop chains, the results are basically the same. Also, biology would prefer the target, and relationships, it would prefer the distraction. But when there are multiple two-hop chains, the result is a little bit controversy because it's not perfectly 1/k. It's prefer the target answer more. And we just conjecture that Llama 3.1 is better trained, and it's probably using a better data set. So the second quantitative prediction would be that if we fine-tune language models on a single distraction, it can actually generalize to all tasks with multiple distractions. So the logic behind our prediction is that if we recall the dynamics of our three-layer transformer, this stage, based on our evaluation, we know that language models stay in this slow learning phase, and it's random guessing between all the answers. And then there will be a sharp phase transition. So we know that a little fine-tuning can just make language models learn the sequential query mechanism through phase transition. And we have reviewed all the mechanisms for sequential query. So we know that this mechanism allows language models to completely ignore all the distractions. Therefore, it could generalize to multiple distractions. So that's the logic of our prediction. So we tried it. We used Llama 2 because it's also a weaker model. And we only fine-tune Llama 2 on prompts with only two-hop chains, which means only one distraction. It might look like this, like A's mother would be, and only with distraction information DEF. And then we would evaluate it on much longer chains, much longer prompts with a lot of distractions. But still, the OOD performance is excellent there. And this kind of prediction is like impossible if we just do the theory or just by our understanding, because always OOD is very hard to understand and very hard to predict. So as a summary, like the circle in the random guessing for two-hop reasoning is that we observe the the distraction would affect the performance in language models, and we simplify it to three-layer transformer. And even I didn't show it here, we even simplify it to three-parameter model. And then we make the prediction that the length generalization for the fine-tuning and also the 1/k between all the answers. And we can verify it in language models. And that's for the two-hop reasoning understanding. Any questions so far? Okay, so the second understanding with this methodology is the active-dormant mechanism. And this is a very intriguing phenomenon in language models. So let's look at the inner structure of an attention head. So we would look at three values. The first is the residual state and the value state, and also the attention rate. So here we visualize the attention rate with a lower triangle matrix. So like for example, this third row, like A31, is the attention from the third token to the first token. And the upper side is 0 because of causal mask. And each time our residual state gets updated and adding by the attention rates times value states. And there's some very intriguing observation in practice is that there are many extreme values for the three things that I just mentioned. So for attention, you see the first column is an outlier. And for the residual, also there's an outlier in the first column. And also this is the norm for the value states. There are some two outliers that are extremely small. We would summarize these observations as extreme token phenomena, which means that actually given any prompt, and here we just use a fixed prompt, which is summer is warm, winter is cold, and we randomly pick 4 heads in Llama 3.1. And you can see here are their attention patterns. And basically all the attention weights are concentrated on the first column. And the second thing, we call it value state strings, because like if we look at the norm for the corresponding value states, the norm for the first token, the BOS token, is actually extremely small, being 0, and all others are among like 3 to 5. And the third thing, we call it residual state peak, because if we look at the norm of the first token, the hidden state norm of the first token is actually extremely large in middle layers, around 500. But for all other tokens, they are around like 20 or 50. So these 3 things combined together, we call it extreme token, because they always happen on the same token. In this case, it's the first token. And our goal is to explain why this appear in language model. So I'm going to present the conclusion first. The conclusion is that this actually comes from an active-dormant mechanism. So let's do some basic algebra here. So the output is attention weights multiplied with value states for each time. So let's transpose the value states so that the attention output is just matrix multiplication between these two, between attention weights and the value states. So you can see the first output for the first token is just A11 times B1 transpose. And second row would be this. Let's take the attention sink phenomenon and look at this specific head. What can we get by doing the algebra? So remember that we have also small value states for the first token, which means that for all those rows that have attention sink on the first token, they are essentially just outputting 0. And we would call this phase as the dormant phase. But only at the 5th row, you see that the attention is concentrated on summer, not on the first column. It's outputting something non-zero, outputting a large norm. And only in this phase, this attention head is active. This is the conclusion. And I will show how we reach this conclusion step by step. So of course, we will go to a very synthetic setting and consider some small models. And in this case, it's a 1-layer transformer. And surprisingly, it can actually recover all the extreme token phenomena. So like this phenomenon is not something special for super large models. We can recap it even in 1-layer transformer. And here's the data we consider. So we always have a BOS token at the beginning, and then we would just do the bigram task, which means that we just sample each next token by Markov transition. And as long as we meet the bycopy tokens, like the trigger tokens, in this case it's T here, then we would copy the token in front of it to the next position. So here V to the next position, U to the next position. And that's our data. We train a 1-layer transformer on it. And here's the result of the 1-layer transformer. So given this fixed prompt, we can observe the attention sink, and also we can have the value strings for the first token. And also, the 3 takeaways in our experimentation should be, firstly, we show that exactly how active-dormant mechanism works here. And second, we can actually have some theorem to give us the prediction that attention logit can grow in logarithm scale, and value state norm would always decrease. And the third thing is that Adam, the optimizer could give us a linear growth for the norm of the BOS token along the training dynamics. So the first takeaway, what exactly is active-dormant mechanism here in this synthetic data set and the one-layer transformer? So look at this by copy task. Actually, it's fully in context. So the trigger token only needs to copy the token in front of it to the next position. So which means that it is actually completely handled by the attention head. And we can see the attention pattern here that all the attentions are concentrated on the token in front of T. And which means that attention head is super active on trigger tokens. It's actively contributing to the result. And this background task is just doing Markov transition. It's just remembering a Markov transition. It can completely handled by our MLP layer. So it's just remember all the Markov transition probabilities for the non-trigger token. And at the same time, on all the non-trigger tokens, all the attentions are on the first token. So the attention head is just outputting 0 on those tokens, and which means that they are being dormant on non-trigger tokens. So we can draw the conclusion that attention sync is just a dormant phase of attention head. And the takeaway too is that we actually fully analyze the formation of extreme token along the pre-training. And okay, this is a bit messy in this figure. I would only focus on the phase 2. It's the training dynamics. Oh, sorry, it should be one-layer transformer. It's a typo here. It's some progressive measures for the training dynamics of one-layer transformer. What can we find here? Actually, this is our one-layer transformer. We can simplify it to a more constrained attention, a more simplified model. So here, we only focus on the attention logics, which is the pre-softmax values on the first column, and we denote them as alpha here, and also the value states of the BOS token, which is the beta here. We can have some theorem is that if we consider the gradient flow of alpha and beta, we can observe that, or we can prove that alpha will grow in the log T scale, with T being the training steps. So which is exactly the case in the transformer, in the one-layer transformer, because here we rescaled our x-axis in log scale. So from 1000K to around 10,000K, it's approximately linear, which means it's approximately log scaled increase. And this alpha corresponds to our attention sync. And you can see from this restricted attention pattern. And the second theorem is that beta would monotonically decrease, which means that the norm for our BOS token would monotonically decrease, which is also exactly the case in the training dynamics of our transformer, which is this purple line. It's just monotonically decreasing. And the third thing is that we have proved that all the values on the first column, eventually they should be a constant. They should always be the same, which we will show later. Okay, the third takeaway is also related to our mysterious optimizer, which is Adam, is that actually it makes the residual state norm to have linear growth along the training dynamics. So here we just check the norm of the residual state for the BOS token along all the checkpoints from 0 to 10K step. So using Adam as our optimizer, it can actually have a linear growth. But if we use SGD, it's just basically remain the same. And also, if we don't use softmax, then we don't have the active-dormant mechanism. Then it's still basically not changing. And why this happens is like some intuition is that because Adam is can adaptively change the learning rate, so it can make small gradients to actually be constant. And there's some simulation, like in a very toy example, like the loss is just like this. And we start with x0 being 10, which means that it's already nearly 0. And by running Adam, we have a linear growth for x. But by running S3D, it's basically stayed the same. And you can see like these two figures are actually pretty close to each other. And that's the intuition. Okay, and so the takeaways in shorter version is that firstly, there's active-dormant. Sometimes attentions are just doing nothing. And also, quantitatively, along the training dynamics, the logic should have logarithmic growth. And the value state norm will just decrease monotonically. And the third thing is that Adam could make the norm of the BOS token to have linear growth along the training dynamics. Then let's go back to large language models. And also, as we promised, we need to check every predictions in large language models. So the prediction one is that we can actually zero out a sync attention head. So what does it mean? Actually, we found some special head in Llama 2 7B. And when we give it GitHub data, so the attention pattern would be super messy. But we just give it some Wikipedia data, we can find that all the attentions are concentrated on the first column. So which means that this head has pure attention sync in Wikipedia data, and it's being not attention sync in GitHub data. So based on our understanding of active-dormant, we would know that if we make another round of forward pass with the same data, but when we reach this head, we just skip it, or like we just zero out the output of this head, it wouldn't affect its performance on Wikipedia, but would affect it a lot on GitHub, right? So here's the result. The x-axis would be the mean attention rates on our extreme tokens. So when it's closer to 1, it means that we have more attention sinks. When it's closer to 0, it means that it's like the attention pattern is more messy. And our y would be the loss increase after we like zeroing out this head. So we can find that on Wikipedia, if we zero out this head, the loss is basically has no change. But on GitHub, if we zero out this head, the loss actually changes a lot. So it's perfectly matches with our prediction, as showing that the attention sync is just a dormant phase. And the second prediction is a very fine-grained quantitative prediction based on our theorem, is that our attention logic on the extreme token, which here is like the key I would be like other tokens, transpose fit our query. Oh, sorry, I'm so sorry. It should be key of the BOS token fit with query of others. It should have a log-scaled increase stage, which is exactly in this part from 10K to around 80K. The logic values are increasing in log scale. And on the other hand side, at the same time, the value state norms are monotonically decreasing here. And here, this is the training dynamics for almost 7B, and we just give them fixed prompt and compute these two progressive measures along all the checkpoints. And another part of this prediction is that when the attention logic stops increasing, or like it reaches a stable phase, the value state for the BOS token should also reach a stable phase. So they would stop increase and stop decreasing together. which is also predicted in our theorem. And the third thing is like it's a tricky thing, is that normally we would consider the attention weight, but if we look at the attention logit, the pre-softmax values, the first column here, in our theorem, we predict that it actually should be a constant. And we can immediately find here, like the first column has basically the same color here, but all other columns has very diverse colors. So which means that the first column is basically a constant in all attention weights. And we can actually verify this more rigorously by computing the standard deviations of each column. But this could already give us an idea of that the first column is just constant. And this is true for any prompt. And our fourth prediction is that the norm of the residual state should have a linear growth along the training dynamics. And here's the checkpoints for llama, so for almost 7B. And still given fixed prompt and compute the residual state norm along checkpoints. And you can find it. It's exactly a linear scaled increase for the norm of BOS token. So as a summary, it's like we have all these three intriguing phenomena. They are very extreme, like all the attention sinks and value state drains and residual state peaks. And we explain them with our active-dormant mechanism. And we have theory, we have our experiments in synthetic data sets, and everything got matched in language models. Yeah, so this basically it for this active-dormant mechanism. So just to wrap up, we promised that we want to work on the circle, and we want to give exact matching quantitative results between small models and large models. And in both of these two cases, two-hop reasoning and the active-dormant mechanism, we have reached this goal. And it's kind of a new methodology that many theorists have ignored because we only focus on small models, but actually we show that it's doable to show the exact matching between small models and the large models. And it can leave us many useful predictions for language models. Yeah, and that's it. Thank you so much.
Yeah, thank you. I have a quick question about the first paper. So you study a three-layer transformer, and
Yes.
I was wondering if there is any existing study that explore the role of the second and third layers. You said that the first layer is the induction head. What about the second and third?
Oh, right. So do you mean like the study by empirical side or study by theoretical side?
Both are fine.
Okay, so like the point is that there are some like theoretical understanding for what these two heads are doing, and they prove some theorems for it. But what we have shown is that they actually do not match with the real case. And I think like this two-hop reasoning problem is getting pretty popular recently in theory community. And I think Jason and a bunch of other theory people has just come up with some papers on it, but I haven't checked out them.
You actually have a question. So you're saying the constructive proof of this paper does not work? What do you mean by like does not work? Is the proof incorrect or something
they
else?
construct something,
yeah.
But if we train the transformer, it leads to a completely different mechanism compared to their construction.
I see. I guess I assume that that paper is claiming something that the transformer can represent this function, but doesn't claim whenever you train empirically, you will always get that, right?
That's true.
And you find out that it's not the case. empirical
Yeah,
stuff.
that's I'm agree with that.
Okay.
Thank you.
Yeah, that's the thank Tianyu again. Thank you.
Thank you.
Thank you so much.